Hey everybody, it's Dr. Morgan. I'm having a little trouble with my green screen setup today. It doesn't like the color red of my shirt and it's throwing off the white balance, so if I disappear, you'll know why. As we get to the point where we're talking about the very, very early universe, just seconds, maybe even nanoseconds after the Big Bang, we have to understand something about the fundamental theories of the particles that exist in the universe and their interactions with one another. So what I want to try to do today is to just give you a hint of that, and over the next few videos to talk about what we think we know about the most fundamental constituents of the universe. The question of what things are elementary dates all the way back to ancient Greece, where people talked about atoms as being the smallest, most indivisible pieces of matter. We've probably all seen this thing in our chemistry classes. We call it the periodic table of the elements. What do we mean by that? What do we mean when we call these things elements? What we mean is in the 1800s, people thought that these things were elementary, that a carbon atom could not be broken down into anything smaller. In fact, the word atom from the ancient Greek, tomos is the verb that means to cut. So atomos means not able to be cut. The idea of an atom was that it was the smallest possible thing that could exist in nature. And when we tried to simplify things chemically by breaking them down into smaller and smaller and smaller bits, we found certain substances like carbon and sodium and potassium and iron and gold and silver that we couldn't change chemically into anything different. So we consider these things elementary. So we call this thing the periodic table of elements. We learned in the early part of the 20th century that this is not true, that atoms are made of smaller things still, protons and neutrons and electrons. And a carbon atom is 6 protons, 6 neutrons, 6 electrons, and a nitrogen is 7 protons, 7 neutrons, 7 electrons, and an oxygen is 8 protons, 8 neutrons, 8 electrons. And so these things are not fundamental at all. They're different arrangements of something simpler. So how do we think about atoms? If you go to Google and type an image search for atom, you get this kind of picture of an atom like it's a little solar system. There's a little nucleus in the center that has protons and neutrons, and then the electrons kind of orbit around the nucleus like planets orbiting the sun. That is not true. You can't really think about an atom that way. Well, you can think about an atom that way, but you're not capturing some of the most important aspects of an atom. To ask what an atom looks like is to actually ask a very misleading sort of question, and to answer it would be to give a very misleading answer. And the reason for that is, if we talk about the structure of an atom and imagine it made of little solid balls, and we say, well, this is what an atom looks like. The protons and neutrons live in the nucleus and the electrons live outside. First of all, the scale of this is all wrong. If this was the size of an atom, the nucleus would be too small to say. The nucleus is a tiny, tiny, tiny speck in the center of an atom. But the other problem is that an atom is very small. The size of an atom is a nanometer or so in diameter. The wavelength of light, the stuff we use to look at things, has a wavelength, visible light anyway, of hundreds of nanometers. Meaning that you can't bounce visible light off of an atom. You can't take a picture of an atom with red light or blue light or green light. In order to see an atom, you would have to use light that has a wavelength comparable to the size of the atom, a wavelength of nanometers. Well, the shorter the wavelength of light, the higher the energy. We've talked about this many, many times. So if I hit an atom with energy with a light that has such high energy that it would be able to bounce off the atom and see what it looks like, that light would knock the electrons out of the atom. They wouldn't be there anymore. They would disrupt the structure of the atom because it would require so much energy to see something that small. So any picture of an atom is not to be taken seriously as an image of what it looks like. You can think of this image of an atom as a little nucleus with electrons swirling around it as being more like a subway map. A subway map doesn't show you what color the car, if you go to DC and look at the subway map, the red line and the blue line, the cars aren't red and blue, the tracks aren't red and blue, they're not all perfectly straight lines, the stations aren't all equally spaced in the city. A subway map is a visualization of the parts of the subway system and how they are connected to one another. Likewise, a picture of an atom with the little nucleus and the electrons going around it is a visualization of the parts of the atom and how they're connected to one another. So let's not take any image of an atom very seriously. What do we know? There are protons and neutrons in the nucleus and in a big space, and then the electrons kind of hanging around the outside of the atom. One of the visualizations you'll sometimes see of an atom is the electron represented as, or electrons are represented as sort of a cloud that surrounds the nucleus. The reason for this is because electrons are very, very tiny. They're smaller than the wavelength of light. Because we can't bounce light off of an electron to see where it is, we have to only talk about the probability of finding an electron in a particular location in space. And so we represent the electron as a mathematical function of probabilities of where the electron is likely to be if we go looking for it. There's a whole field of physics invented in the 20th century called quantum mechanics, which is a way to talk about the behaviors of particles that are too small to locate in a definite location in space. So we only talk about their probabilities of being found in a particular region of space. So this electron cloud represents the probability of an electron in an atom being at some particular point in space. So we can't think of it as like a little orbit, but it is the region of space occupied by the electron, and it's hanging around in there doing who knows what. But we know how likely are we. We're very likely to find it here, less likely to find it here. For some reason, not very likely to find it here, but likely to find it here again. And so this is a map of the probabilities of finding an electron in a particular location in space. We can't really get too deeply into quantum mechanics in this course as much as I would love to. We just don't have the time. But what we will do is talk about some of the theories that have arisen to talk about subatomic particles and their interactions with one another. Now, if this was 1920, we would think that electrons and protons are fundamental. Like, neutron wasn't discovered until the 1950s, I think. If it was 1950, you would think protons, electrons, and neutrons are fundamental. So this question of what are the smallest things and which ones are fundamental is what we're going to be getting at in the next few lectures. One thing we do know about subatomic particles, especially charged particles like electrons and protons, is they exert forces on one another. The thing that holds an atom together is the electrical attraction between the positive protons and the negative neutrons on the outside. If I have two electrons close to one another, they will push one another apart. So we know this probably from some elementary school or middle school science class, that things with opposite charges attract one another, things with like charges repel one another. So if I have two electrons in space, and even though electrons aren't little balls, because I have to draw them as something, I'm going to draw them as little balls. If I have two electrons a nanometer apart, they will exert a force of electrical repulsion on one another. We've known this since we knew there was a thing called electrical charge back in the 1700s with Coulomb and people like that. The question is, what is happening there? What is this thing called charge, and what is the cause of this force? The thing to recognize about the idea of a charge and a positive and negative charge, what does that mean? What does it mean to say a proton is positive and an electron is negative? These are just words. These are just labels that we've given to a fact about them, which is sometimes they attract and sometimes they repel. Charge is, as far as we know, just a property that electrons have and that protons have. It's not some extra thing that's sprayed onto the electron. An electron without any charge wouldn't be an electron. The charge is fundamental to its identity as an electron. Why do two electrons push each other apart and an electron and a proton pull each other together? That's just what electrical charge does. That is a fundamental, as far as we know, a fundamental interaction that happens in the universe. What causes it? Well, in the 1800s, we used to talk about something called an electric field. An electron creates an electrical field, and the other electron creates an electrical field, and they're each sitting in the electrical field of the other, and that pushes them apart. But what is an electric field? Like, is it a thing? Is it a kind of stuff? Is it a substance? Is it some kind of entity that exists in the universe separate from the electron? We didn't really have a good answer for that in the 1800s. In fact, we didn't really have a good answer to that until the middle of the 20th century. How do we think about the reason that two electrons push each other apart? What's actually happening in space between two electrons? Well, the way we think about it now in the 21st century, and since the middle of the 20th century, is to imagine that two electrons are exchanging energy. And they're exchanging energy in terms, or in terms of the energy of some field. That field is called the electromagnetic field, and a little bit of energy of an electromagnetic field is called a photon. We have probably used the word photon in this class a bunch of times before, talking about light, and that's what light is. Light is a phenomenon of the electromagnetic field, and a little bit of energy of the electromagnetic field is called a photon. You can think of a photon like a little particle that bounces back and forth between the electrons, but that's not exactly right. It is a quantum, a individual chunk of energy carried by the electromagnetic field. But to visualize what's happening between two electrons is two electrons, if they're close to one another, are exchanging energy in the form of photons of light. If you want to picture this in some kind of analogy, one thing that you can picture is, imagine two people on skateboards, and they're standing 3 feet apart from one another, and they're playing catch with something really heavy, like bowling balls or cinder blocks. What will these two people do as they toss bowling balls back and forth? Well, if I'm on a skateboard and I throw a bowling ball this way, I'm going to roll back the other direction. And if I'm over here and I catch a bowling ball, when I catch that bowling ball, I'm going to roll back in the direction that the bowling ball was moving. So if we imagine two people on skateboards throwing bowling balls back and forth, what will they do? They will move apart from one another because of the momentum carried by those bowling balls. This is kind of a way to think about these exchange forces in quantum mechanics, that the electron and the other electron are exchanging energy by tossing photons back and forth between one another. And the momentum of those exchange photons pushes them apart. And that's what electrical repulsion is in these theories that describe what are the interactions between these fundamental particles. Those theories are called quantum field theories. And quantum field theories discuss two kinds of particles. There are matter particles, particles that make up stuff like protons, neutrons, electrons, neutrinos, etc. And there are force-carrying particles. They are the particles that get tossed back and forth between particles, and their momentum gives rise to attractive and repulsive forces between them. So an electron is a matter particle. A photon of light you can think of as a force-carrying particle, a force-carrying bundle of energy of the electromagnetic field. Quantum field theories arose in the 1950s or so, and this particular quantum field theory that describes the interactions between electrically charged particles and the electric field or electromagnetic field is called quantum electrodynamics. Another thing that comes out of quantum field theories, when you add the theory of relativity to them, and this is getting a little deeper than we're going to be able to go to understand how this happens, but when you take a quantum field theory and you make it obey the rules of Einstein's theory of relativity, the whole E equals mc squared business, it turns out that for every particle in a situation with positive energy, you have a requirement that there be the same sort of particle with the negative energy. And this gives rise to the idea of antimatter particles. There's nothing magical or science fiction about antimatter. There are particles called electrons that have a negative charge. There are also particles called positrons that have a positive charge. The only difference between an electron and a positron is that one is negative and the other is positive. And for some reason, our universe has a lot of electrons in it and not a whole lot of positrons in it. That is a fact about our universe that needs explaining. Because if we make an electron in a particle accelerator, we always make a positron also. You can't make an electron by itself, and you can't make a positron by itself. You have to make them in pairs. And that means that at some point in the history of the universe, that rule was broken. If that rule wasn't broken, the universe would have the same number of negative electrons and positive positrons. Well, it doesn't. The universe has lots and lots and lots of these, and very few of those. Where'd they all go? Really good question. We'll talk about that in another lecture. So we know that particles exist. We know that antiparticles exist with the opposite electrical charge. And we know that force-carrying particles, the technical term for matter particles is fermions, and force particles is bosons. A photon is a boson, an electron is a fermion. And quantum electrodynamics is a complex mathematical theory that describes how these things interact with one another, and it is very effective. It can make predictions of the interactions between charged particles that are accurate to 1 part per trillion, okay? Accurate to the 12th decimal place, one of the most accurate theories we have ever devised about nature. In confirming that this theory was true, we started discovering that there are other particles in nature as well that are similar to electrons and positrons. It turns out that the electron has some little friends, actually big friends, that are just like the electron but have more mass. There's a particle that's just like an electron, but it's 150 times or so more massive than an electron. That particle is called a muon. There are also antimuons that are just like a positron, but 150 times more massive. There are other particles that are just like an electron, except they're something like 1,000 times more massive. That particle is called the tau lepton. And just like there's an anti-electron called a positron, and an anti-muon called anti-muon, there's an antiparticle to the tau called the anti-tau, exactly the same particle with a positive charge. As far as we know, these are the only charged leptons, particles like an electron. So there's 6 of them. Electron, positron, muon, antimuon, tau, antitau. We don't know why there are these 3 different electrons, the electron and its 2 heavy cousins, but there are. Okay? We call these families, so these are the 3 families of leptons, electrons, muons, and taus. We talked about neutrinos back when we were talking about supernovas and nuclear fusion and stuff. There are also 3 families of neutrinos. There's an electron neutrino, a muon neutrino, and a tau neutrino. Why? We don't really know. But we know that they also come in 3s, which is interesting. Neutrinos, by the way, they're not part of quantum electrodynamics because they don't feel the electrical force. They're not charged, right? It's right in there in their name, little neutral particle, neutrino. So if we're going to understand what neutrinos do, we need a new theory. Different from quantum electrodynamics, we need some kind of quantum weak force dynamics because neutrinos only feel this force called the weak force. There are particles inside of protons and neutrons that feel another force entirely, called the strong force. So for every one of these fundamental forces, we're going to need a mathematical theory that describes how it works, and we're going to need some little particle that gets tossed back and forth that explains what causes that attraction or that repulsion. We will talk about these other quantum field theories in another video. And once we do that, we'll be ready to look at the big picture and see these are all the fundamental particles we know about. These are all the fundamental forces we know about. And these are the things we believe are truly elementary in our universe. So we'll be ready to talk about that time in the history of the universe way back at the Big Bang when the only thing that existed were elementary particles and the forces between them.